Here we're going to take a look at a couple more examples of applications of integrations. These are what are known as accumulation problems here. But we're using sort of the same underlying principle that we talked about in the last lesson. Basically, we are interpreting the integral here as the amount accumulated or the net change. So we're still using this idea that the integral of some rate of change of some quantity. So if we take our rate of change and we integrate it, the integral of a rate of change is the net change in that quantity, or in the amount of the quantity. And mathematically, we wrote this. We said that the net change, or the difference from the amount that we have at A and the amount that we have at B, where B and A are our two sort of our endpoints, our starting point and our end point. This was given by the integral of the rate of change of that quantity over x as we went from A to B. Okay, so the integral of our rate of change is the net change over that time period, or over that distance, or whatever x represents here. So these kind of examples, well, we can just take a look at them. They involve sort of situations involving various things that have different sorts of rates rather than just position, velocity, and acceleration. So the first one here, the supplier of calculators, a supplier of calculators, has a marginal revenue of 15 minus 5e to the negative x over 50 per calculator when she has sold x calculators. What will her total revenue be? What will be her total revenue if she sells 100 calculators? Okay. So what they're giving us in this question is marginal revenue. Okay. What does marginal revenue mean? Well, it is the rate of change of revenue at a specific level of production. So it's dr dx, or r primed at x, where r is our revenue function. So we know that in this question, r primed is equal to 15 minus e to the negative x over 50. So that is our rate. So if we want to find the total revenue, we need to integrate the rate of change of revenue, or integrate the marginal revenue, sorry? Did I forget something in there? The 5, yes. All right. So our revenue, marginal revenue, is 15 minus 5 times E there. 15 minus 5 times E. Okay. So we're integrating our marginal revenue function. Now, what are the endpoints going to be of our integration? So where is she starting? Where is she ending here? What does x represent in this question? Well, x always represents the number of units either produced or the number of units sold. What is the endpoint in terms of the number of units sold? 100. What is the starting point in terms of the number of units sold? 0. So we're integrating this function from 0 to 100. We want to know how much revenue she accumulates by the time she sold 100 of these calculators, assuming she starts having sold none of these guys. So now it's just a matter of evaluating our integral. So we need our antiderivative here. Our antiderivative is going to be, well, let's see, we can do this term by term. Antiderivative of 15 is 15x. Antiderivative of this guy here, well, let's see. We're going to need something that is e to the negative x over 50. When we do the derivative of that, that's going to bring down a 1 over 50. So in front, we want something that, when we multiply it by 1 over 50, is going to give us 5. So that's going to be 250. 250 divided by 50 gives us 5. And let's see, we want this to be positive, because when that negative 1 over 50 comes down, we want it to change the sign to negative. And then we are evaluating this from 0 to 100. So if we evaluate this at 100 first, we get 1500 plus 250 e to the negative 1/2. No, wait, e to the negative 2. And then we're going to subtract this thing evaluated at 0, which is just going to be 0 plus 250. Punch this into our calculator. We get 1,283.83. So our total revenue is going to be revenue after selling 100 is $1,283.83. Okay. All right, let's take a look at our next example here. Water flows from a storage tank at a rate of R at t equals 200 minus 4t liters per minute, where we're going from t equals 0 to 50. Find the amount of water that flows out in the first 10 minutes. Okay. So, if we're looking for the amount of water, all right. Well, what is our rate in this question, obviously? So let's see, we want to find, let's say A, the amount of water. Okay. So we need A primed, okay, which is the rate of change of water. What is the rate of change of water? Well, they tell it to us in this question here. They tell us that the rate is, we want the rate at which it's flowing out of the tank. Okay, so our rate here is going to be 200 minus 4t. It's given to us by this function here. So if we want the total amount that is flowed out, okay, they give us the rate that it's flowing out. If we want the total amount that is flown out, what do we have to do? Well, we want to integrate this rate function, a primed at t, over dt, and what are the limits of our integration going to be? Ian? Oh, yeah, 0 to 10, because we want it in the first 10 minutes. So we're just taking our integral here. Again, we can do this term by term. 200t minus 2t squared, and evaluate this from 0 to 10. This one's kind of nice because when we evaluate it at 0, we're just going to have 0. So we just evaluate this at 10. We get 2,000 minus 200. 10 squared is 100 times 2 is 200. Yeah. Do the subtraction, 1,800. So after 10 minutes, 1,800 liters has leaked out.